Hello everyone, welcome to my channel Euclid Mathematics. So today I'm here with the uniform convergence test for series of a function. So in my previous lecture I explained to you all the test for uniform convergence. Then after of that Weierstrass test for uniform convergence. Okay, some of these are for series of function and some are for sequence of function. Now in my today's lecture I will explain to you Dirichlet test. Okay, in my previous lecture I explained Dirichlet test and some of the example on it. Okay, in my today's video I will explain more example on Dirichlet test. Okay? So to understand that topic better, we have to solve more examples. Okay, so I will explain some examples and properties on the Dirichlet test. Okay, so let's get started to our today's lecture. So here, example, it says that series given x raised to n upon n plus 1 and x belongs to closed interval minus a. Okay, and that a smaller than 1. Okay, the value for a it is given here, which is smaller than 1. So minus 1 to 1. Okay, but a smaller than 1, that means it comes open interval. Okay, so let's get the solution started. The solution. So we, as per the definition of a Dirichlet test, we have to convert our series of function in the form of two different function like u and x and v and x. Okay, so I did it here. u1 of x is equal to x raised to n and v of x is equal to 1 upon n plus 1. So you have to choose here u and x, v and x very carefully, as we want one of them is monotonically decreasing, and as n tends to infinity it goes to 0. Okay, and other one is the sequence of partial sum need to be uniformly bounded. Okay, so I consider here u and x as x raised to n and v and x is upon n plus 1. Okay, so when we apply limit n tends to infinity, v and x, we get the 1 upon n plus 1 means 1 upon infinity plus 1, which is 0. Okay, that means we can see that v and x as monotonically decreasing and uniformly convergent to 0. Okay, so it goes to 0. So v and x satisfy the first property, and other one x raised to n it is given. Okay, and x which belongs to closed interval minus a to a, and the value for a which is smaller than 1. Okay, and when we apply limit n tends to infinity, we can see that it is the part of a smaller than 1 element. Okay, and when element is smaller than 1 and it goes to the infinity, we know that that term going smaller and smaller. Okay, so here let's see how it goes smaller. Okay, so u and x I expanded here, x mod x plus mod x raised square plus mod x cube plus mod x raised to n. Okay, just run the value for n 1 to n. Okay, so I got it here. And we know that x is from that interval, so let's consider some value for x. Okay, so I consider x as a plus a square plus a cube plus a raised to n. Okay, I just replace the value of x is a. Why a? Because x belongs to that interval, and that interval contain a type of element. Okay, and a is smaller than 1. Okay, so we can observe it here, a plus a square plus a cube plus a raised to n. It is a geometric series. Okay, so you all have learned geometric series already. Okay, and sum of a geometric series, we know that how to find sum of geometric series, sum of all geometric series. We want to get some fixed value that we apply n tends to infinity to our sequence of function. Okay, series of function. So we can see that if we have that series like this, a plus a square plus a cube plus so on. Okay, then we write there sum of a geometric series. First term it is here upon 1 minus common difference between the all elements. Okay, so first term it is here, and upon 1 minus common difference between these two elements is a. Common difference, how to find? A square divided by a, it is the common difference. A cube divided by a square, it is common difference. So we get the constant a only. Okay, so we can see that the geometric progression it is given here. So there is sum of nth term, it is a 1 upon 1 minus a. Okay, sum of all series 1 upon first term upon 1 minus common difference. Okay, so we can see that which is uniformly bounded. Why it is uniformly bounded? Because a which belongs to that interval, and a is having the value smaller than 1. If a is smaller than 1, then that means this value is going to be a smaller and smaller. So it gives a bounded value. Okay, this is the uniformly bounded. Then we can say that first property hold and second property is also hold. Then it's a sum of a partial sum, we get the equals uniformly bounded. Okay, so then we say that our series of function x raised to n upon n plus 1, which is a uniformly convergent on closed interval minus a to a and a smaller than 1. So here in my second video, I taken next example minus 1 raised to n minus 1 upon x into x raised to n, and that x belongs to closed interval 0 to k, and k is strictly smaller than 1. Okay, k strictly less 1. And then we have to check it out whether that function, series of function is uniformly convergent or not. Okay, so it is easier to find out. Okay, so in my in our definition it says that one of them need to be a uniformly bounded and converges to 0 uniformly. Okay, and another one is need to be a sequence of partial sum. Okay, it need to be uniformly bounded. So you have to apply the definition for Dirichlet test only. Okay, so you can see that I shown here that minus 1 raised to n minus 1, for even value it goes 0, n value odd value it goes 1. Okay, so it is bounded between 0 and 1. Okay, and remaining one x raised to n in interval close 0, open 1, it goes to the 0. As n goes to infinity, it goes to 0. Okay, so it monotonically decreasing and uniformly convergent to 0. Okay, so then we can say that minus n raised to n minus 1 x raised to n, and that x has interval here, which is a uniformly convergent on our interval here. Okay, so everything is depend on these intervals. We have to be very careful about these intervals for finding uniformly convergent. Okay, so here you can see one remark here, okay, which is a Leibniz test. So Leibniz test is the previous part. Okay, so Leibniz test, it says that if you have a function which is like a minus 1 raised to n into some of the function, okay, it is alternating series. Okay, minus 1 raised to n means it is the alternating series. It gives plus minus value, and other one is function it multiplied there, so which converges to 0. Okay, so if this type of the series are there, so we call it as a Leibniz test. Okay, Leibniz test for alternating series of a real number. Okay, this is a particular case for that Dirichlet test. Okay, it is a particular case for that Dirichlet test. I hope so you all have understood my today's example and my previous Dirichlet test video. Okay, so if you have any doubt, you can ask me in comment section. Okay, I hope so you all have understood my today's lecture. Thank you everyone. Thank you for my today's lecture.